period. Suppose if I start my measurement here, the place to stop is this. Okay. For a sinusoidal waveform, these values will be same. This T1 if I write and T2 if I write here, they are the same. So in defining time period, we say that it's time taken to complete one cycle. Now, what is one cycle? One cycle is that part of the waveform, which keep repeating itself. Let's go to the next definition, frequency, and these two are connected. You must be knowing the relation between the two. T is equal to 1 by F. Frequency and time period are reciprocal of each other. What is frequency? This is something like, how frequently the buses arrive at our bus stop. We say less frequently or more frequently. Number of cycles per second. So CPS, cycles per second. Now the unit, SI unit is hertz. So if we say the frequency of AC is 50 hertz, what's the meaning? 50 cycles per second. Okay, so that's the meaning. So if you write here time and number of cycles, and if I say time taken to complete one cycle is, this is number of cycle, N, is time period T. What is frequency definition? Number of cycles per second. So in 1 second, how much? So it has to be 1 into 1 divided by T, no? So that is your frequency. That's the relation between frequency and time period. So then this is known to you. Just now we said what is instantaneous value V? V is equal to V naught sine omega t, or it can be V naught cos omega t, or V naught sine omega t plus any angle phi or minus phi, whatever it is. Okay. So this is the instantaneous value. Then the peak value. Peak value is also known as amplitude. Remember, peak value is also called as amplitude, and it's denoted by I naught for current, and for voltage it is V naught. Okay. Amplitude, peak value, the maximum value taken by AC quantity in any half cycle. For example, in this diagram, which I have drawn already, this is my peak value. If this is voltage, then this is V naught. Correct? If this y-axis is V, and this is T, let's say, or omega T, whatever. So V naught. If this is V naught, this also is V naught. And from here to here, that is from here to here, it is always referred as peak to peak value. So there is a relation between, I'm writing at the bottom here, peak to peak value. What is peak to peak? Peak to peak is 2 times the peak value. From negative peak to positive peak, or positive peak to negative peak. That's called peak to peak value. The mean value or the average value. The next one here. Average value of AC taken over a complete cycle is 0. So Vm is always 0 for the entire cycle. So therefore, it is not defined for the entire cycle. It is measured over half a cycle. So the average value over half a cycle, you all must be knowing, Vm is equal to 2V0 by pi. Or Im was also equal to 2I0 by pi. Okay. So that's the definition of average value. Remember, average value is defined over half a cycle. It is not defined over full cycle, because over full cycle the value is going to be 0. Next comes the most important term in AC, and that is RMS value. Let me erase a few of these to write about RMS. RMS is root mean square. So as I say, I will write, because this is important according to me. Very nice question can be framed always. Root. So let me write the root. And the next word is average. So I will divide it by 2 pi. Because for the entire cycle, the angle is 0 to 2 pi, no? So the base is 2 pi. So average. Because RMS value is the only value which is defined for the entire cycle. Because mean value is defined for half a cycle. Amplitude is for any half cycle, no? Either positive half cycle or negative half cycle, value is same. Its RMS value is the only one which is defined over the entire cycle. And its full form is square root of average of square of the instantaneous values taken over, that is integration, summation, no, over the entire cycle. And I'm doing it with respect to theta, integrating with respect to omega t. And you all know what is the full form of V here. It is V naught sine omega t, the whole square here. And therefore, if you solve this, this is a very easy sum in mathematics to solve. The value is going to be V naught by root 2. And that's what we know, no, as RMS value. Vrms is always equal to V naught by root 2. So once again, let me repeat, RMS is nothing but root of, as I showed you here again, root of this one, root of average of square of the instantaneous values taken over one complete cycle. That is integration. And you know how to integrate sine omega t, sine square omega t. Sine square omega t will be 1 minus cos 2 omega t by 2, and therefore that by 2 will come. All right, here, and then you have to integrate with respect to omega t, and you have to substitute 0 to 2 pi, the lower limit and upper limit. In any case, when you do it, you will get it as V0 by root 2. Good. So that's going to be the answer of VRMS. So the last one is phase of AC. And the phase of AC can be defined this way, no? This is the better picture maybe. So we are having T along the x-axis, to say V or I. You know that the entire time taken is time period T here. So half of that will be T by 2, half of that is this much is T by 4. How much is this? This is T by 2. And this is 3T by 4 here. So phase can be defined at any point. A, B, C, D, whatever any point. Let's say I want to define phase at B. And this graph is V. The dotted graph is of I, let's say. So the bold one is V and the dotted graph is of I. What is the phase of V at B? It's T by 4. Similarly, phase of I also at B is also T by 4. Because as you can see, V and I are in phase. That means, what is the phase difference between the two? T by 4 minus T by 4 is 0, no? So the phase difference between the two is 0. Before we say here, V and this diagram especially, V and I are in phase. But what is phase? The amount of time lapsed or angular distance covered once an AC quantity has passed a given reference point, and the reference point is always 0 in the positive direction. So what is the time lapse to reach from A to B? It's T by 4. So that is the phase of both V as well as I at B, T by 4 and T by 4. So therefore the phase difference is 0 degree. And you all know that this is what we will get when AC is applied to pure R. Okay, V and I are in phase. There is no phase difference. So the definition of phase is the amount of time lapsed or the angular distance covered once an AC quantity has passed a given reference point, and the reference point is usually 0 in the positive direction. And yes, phase difference is very important then. Phase difference is difference in phase between the two quantities. So if the two AC quantities rise and fall simultaneously, we say that they are in phase. If they don't rise and fall simultaneously, we say that they are out of phase. When they're out of phase, we know that somebody has to lead, somebody has to lag. It's like two students running the race. So if they run in phase, then both will win. Correct? No, there is absolutely no time difference between them or not even the distance difference between them. So they are running in phase. But if one runs ahead of the other, surely you will say that student A is leading student B. You can say either in terms of time or in terms of distance. Student A is leading student B by a time of, let's say, 2 seconds or by a distance of 1 meter. So one is leading by 1 meter means the other one is lagging by the same amount. No? So here also, when it is out of phase, we always say if somebody is leading, other one is lagging, but by the same amount. Okay, you can describe that either in terms of time or in terms of angular distance here. So therefore, we know now AC can be applied to resistor, capacitor, and coil. Let's start with the AC applied to resistor. You all know this diagram very clearly that it's a pure resistor. So, and we apply AC to that, and this is how the sinusoidal generator is shown as. This is either V is equal to V naught sin omega t, let's say. And we need to find out the expression for current, I. I at any instant will be definitely V by R, and V is definitely V naught sin omega t by R. And this V naught by R will be written as I naught. So therefore, I will be equal to I naught sin omega t. And that's what I have written. For V is equal to V naught sin omega t, I will be equal to I naught sin omega t. How do we calculate the average power? Of course, power at any instant P of t will be equal to V of t into I of t. So this will be V naught sin omega t into I naught sin omega t, instantaneous power, no, current and voltage. So this will be V naught I naught sin square omega t. Now if I want average, and this is how the angular brackets are used to represent average, okay? So this means here, it's average. Average value. Now V naught and I naught are constants, remember, they are amplitudes. They don't vary with time. The only quantity that can vary with time is this sin square omega t. Therefore, I put average only for this. That's what we have done here. Correct? So V naught I naught into sin square omega t, and that is nothing but, the average value of the sin square omega t, average value of sin square omega t is half always. So how to do it? You must be knowing the average value of anything can be defined this way: 1 by t integral 0 to t, P of t dt. This is the average value of power. So if you are measuring sin square omega t, again sin square omega t is 1 minus cos 2 omega t divided by 2. So that 1 by 2 will be remaining. Remaining becomes 0 there. So this will be equal to V naught I naught. The average value of sin square omega t over the entire cycle is 1/2. So that is 1 by 2. This can be written as V0 by root 2 and I0 by root 2. Let me know what is V0 by root 2. It is VRMS. And I0 by root 2 is IRMS. That means P average is equal to VRMS into IRMS. But also, you know that VRMS is IRMS into R. Therefore, it can be also equal to I square RMS into R. Correct, no? Right? So also it can be, if you want, IRMS can be written as VRMS by R. So it can be V square RMS by R. So these are the expressions for power, when AC is applied to pure resistor. So is there average power? The answer is yes. And the power is dissipated in the form of heat, in a resistor. It's only the resistor which dissipates power, in the form of heat. It dissipates. Its loss of energy is there when current moves through a resistor. But in case of capacitor and coil, we know that it stores energy, and the power dissipation will be always 0. The average power dissipation is 0. So we will see that in the next slides. This is all about power applied to a resistor. In case if I have to show you with the help of graph also, it is possible. For example, I will erase this little so to create space in this slide. For example, now, so this is the picture of, the voltage, let's say, and current is this only, no? They rise and fall simultaneously. You know that current and voltage are in phase. Now here, if I have to write the graph of power here, I can divide this into can say 0 to 90, 90 to 180 angle, then 270 here, finally 360. Tell me in 90, both V as well as I are positive. No, therefore, positive into positive, you should get positive only. In second quadrant also, I'm sorry. So 90 to 180 also both are positive. Therefore, positive into positive should be positive only again. Here, again, negative into negative should give you again positive only, right? Because power is V into I. Instantaneous power is V into I. And here also again, minus into minus, again it is positive. So is there an average value for this? The answer is yes, which is not 0. So the average value is not 0 for a resistor. That's what I wanted to say. Phasor. Now this is very important. Phasor is a rotating vector. Like vector has got both magnitude and direction, but phasor shows you only magnitude and maybe phase. This is the phase. See here, this is, let's say, I naught, and this is V naught. V naught and I naught are in phase, we say. Why? Because both of them have the same phase, no? Omega t. But in case if you write the diagram, let's say, this is I naught, and this is your V naught. Then this, let's say, angle is 90 degree now. Now we don't say that, they are in phase. I naught and V naught are not in phase. They are, or I and V are not in phase, but they are out of phase. Current leads. This one leads V by 90 degree, I by 2. So phasor is a rotating vector. At any point, it gives you two things. One is the magnitude as well as the phase. Similar to a vector which shows magnitude and direction. Here, not direction but phase. Now coming to AC voltage applied to an inductor. Inductor is nothing but pure inductor coil. That means it has got self-inductance L, but R of this is assumed to be 0, pure. Very difficult to find one, but we'll have to imagine. When AC is applied to this, what happens? We all know that there is induced EMF in the coil, which is equal to magnitude. If I take, it's L into di by dt, correct? If di by dt is more and more, E is also more and more. All that we know. So trying to find out current expression here. If V is equal to V naught sin omega t, remember, whenever AC is applied to a coil, current lags. And opposite is the case when AC is applied to a capacitor. Current leads. Whether it is pure coil or impure coil. What I'm trying to say is, let's say this has, now we said that this is a pure coil. Even if it has some resistance, I can show that in series. And if I ask you a question, in this current lags or leads the applied voltage, your answer should be very confident lags. Whenever there is a coil and coil alone, along with the resistor in AC circuit, current has to lag. Current cannot lead. By what angle? If it's a pure pure inductance, then the angle is exactly 90 degree. But if at all, if there is a resistance, then it cannot be 90. It has to be written as omega t minus 5, where 5 value can be anywhere between 0 and 90. Okay. So instead of saying current lags, can I say V leads? That's what I said, no? At time student A. leads student B means student B is lagging student A by the same amount. So either I can say I lags V by 90 degree, or applied voltage leads the current through the coil by 90 degree, or pi by 2 radians. Okay. In defining all this, we get I naught as equal to V naught by XL, not R. And what is this XL? XL is the reactance. Reactance. Okay. And reactance is nothing but the opposition offered by the coil to the flow of AC. Reactance in general is the opposition of the reactive circuit elements, either capacitor or coil, to the flow of alternating current. Resistance is the opposition offered by the resistor to the flow of current. No, so reactance is the opposition offered by the reactive element, which can be either coil or a capacitor, to the flow of AC. And XL will be equal to omega into L. And what is omega? Omega is angular frequency, and that is 2 pi FL. As frequency increases, even XL also increases. As frequency decreases, XL also decreases. So what is XL if frequency is 0? XL is also 0 ohm. Remember, the unit of reactance is same as that of resistance, and that is ohm. So which means, F is 0 for DC, constant. F is 0 only for constant things. Correct? So in DC circuit, what is the reactance offered by the coil? 0. That means it allows DC. Coil allows DC, but it opposes only AC. And the amount of opposition is 2 pi FL. So to which frequency coil opposes more? Higher frequencies. Because if F is more and more, XL is more and more. If F is small, then XL is also small. So therefore, we say L allows DC, but L opposes AC. But opposition is low for less frequency. The opposition is high for high frequency. Because XL is proportional to F. Okay. So we know, therefore, one thing: whenever there is coil in a circuit, only coil, not capacitor. I mean, when both are there, we have to find out whether current leads or lags. It depends on something else. But if you find only coil along with resistance and all, you should be confidently saying that current lags in that circuit. And if it is a pure coil, current lags by exactly an angle 90 degree. If there is a resistor along with that, then it is lagging only. Current is lagging only, but by an angle which is anywhere between 0 and 90. Power, yeah, you all know. This is the waveform for, I said voltage leads and current lags. No, this is voltage. If I draw, this is voltage graph. Current graph is negative cosine. Negative cosine will be like this, no? Correct? So minus cos omega t. So this is current. At any instant, you see current lags the voltage by an angle 90 degree. That means voltage leads the current by an angle 90 degree. So this is the, instantaneous power. P is equal to V into I, which is equal to V naught sin omega t into minus I naught cos omega t. So which means it is minus V naught into I naught sin omega t cos omega t. So this will be like, minus V naught I naught. You know that sin 2 omega t, sin 2 theta is equal to 2 sin theta cos theta, no? So what is sin theta cos theta? It is sin 2 theta by 2. So therefore by 2 into sin of 2 omega t. And the average value, when you take average value, so you take average value of only this, because V naught, I naught are constants. So what is the average value of sin 2 omega t over the entire cycle? it is 0. So therefore, 0 multiplied by anything is 0, and therefore you will get this as 0. Once again, to remind you, the angular brackets are corresponding to average. Okay. So that is the average power consumed over the entire cycle. So if you are asking me a question, sir, is there average power consumed, when AC is applied to a coil? The answer is no. So this can be again explained beautifully. If you know that this is 0 degree and this is 90, this is 180, you can draw the graph of P, which is V into I. See, from 0 to 90, voltage is positive, current is negative. That means it is plus into minus will be minus, right? So for power, it is minus. Then what you'll get in the 90 to 180 region, both are positive. So you'll get plus. Again, 180 to 270, what you'll find? Current is positive, but voltage is negative. Therefore, again, minus. And 270 to 360 degree, in both are negative. That means you'll get plus. Minus into minus is plus. No? So minus plus, what is the average? It has to be 0, right? Correct, because for every positive value, there is a corresponding negative value, and you take the summation over the entire cycle and take the average, it has to be 0, right? So AC voltage applied to a capacitor now. It's again a pure capacitor in which the plates are assumed to be, superconducting, and that means the resistance is 0, and the insulator is a perfect insulator, and AC voltage is applied across it. Remember, the current through the capacitor now leads, current leads in this case. So that means whenever you find a capacitor, let's say there is a resistor across this, but you should be confidently saying that current through the circuit, which is the same through resistor and capacitor at any instant, but is it lagging or leading the applied voltage? The answer should be a bold leading. Current leads. So what angle? If it's a pure capacitor, it is by an angle pi by 2. Otherwise, I is equal to I naught sin omega t plus phi, where phi can be anywhere between 0 to 90 degree. Again, here I naught will be equal to V naught by XC here. And this XC will be equal to 1 by omega C is called the capacitive reactance. So here, what is important to note is, last time we said XL is proportional to F. But XC is not proportional to F, but inversely proportional to F. That means both coil and capacitor, they oppose AC. And that's how they have reactance, no? But the reactance nature is different. Capacitor offers high reactance to low frequencies because XC is inversely proportional to F. Whereas coil offers high reactance to high frequencies. So coil and capacitor, though they are very good friends, but they speak a different language. Whatever coil says yes, the capacitor says no. For example, coil allows DC, I said, but capacitor says no to DC. Why? Because for DC, frequency is 0 and XC will be infinity, no? That means highest opposition to DC. It doesn't allow the direct current, steady current to pass through. And that's what we know. Once the capacitor is fully charged, the current to the capacitor is always 0, right? In DC circuits. So it doesn't allow DC to pass through. There is no current. Okay. So coil says yes to DC, but capacitor says no to DC. Coil says, I'll oppose low frequencies less and high frequencies more, but the capacitor says I will oppose low frequencies more than the high frequencies. Power. Once again, the same story. This is current leading, therefore the graph will look something like this. If this is voltage graph, remember current is leading. So this is not minus cosine now. It will be positive cosine. This is the graph. Okay, 0 to 90 degree, 90 to 180. Again, you can calculate 270 and this is 360. So 0 to 90 both are positive. Therefore, power also will be positive. Power is always the product of V and I. So positive into positive is positive. But in the second 90 to 180, it is a positive and negative, therefore minus. In 180 to 270, both are negative, and minus into minus should be plus. And in the last one, current, this dotted is current. This is V. One is positive, one is negative, therefore again minus. So the average of these must be 0, and you will get that. And remember, current is a positive cosine. Once again, the same story. The average value you have to take. Average value I have defined already. It is taken over one complete cycle, 0 to t of the instantaneous values. Okay, dt. This is the definition of average power. Entire cycle means 1 by t. Good. So, which means current is flowing through a coil or capacitor will be referred as AC current. I'm saying will be referred as wattless current. You know why? Because the average power consumed is 0, right? Therefore, this current flowing through a pure coil and capacitor is always referred as wattless current. Wattless current or wattless current. Now, the most important circuit, and that is the LCR circuit. No, this is R, okay? This is L and C. It can be in any order. But remember now both L and C are there. Now, if I ask a question whether I leads or lags, you can't answer it very fast unless we know this omega, which is equal to 2 pi f, and f decides everything. The frequency decides. Okay. There are very low frequencies, what happens? XC will be much greater than XL. At very high frequencies, surely XL will be much greater than XC. But at a particular frequency, F is equal to F naught, you must be knowing that XL will be equal to XC. And therefore, they will cancel out and only resistor dominates. So here capacitor dominates, here coil dominates, here resistor dominates. So that means all have a role to play, resistor, coil and capacitor. But when coil is going to control the current at very high AC frequencies, when a capacitor is going to offer highest opposition to the flow of AC current at very low frequencies. But at a frequency called resonant frequency, which is one single frequency, neither the coil or the capacitor, they offer reactance, but their reactances will be equal and opposite. If one is in the positive y direction, other one will be in the negative y direction. Therefore, the net, if two vectors are there, if I ask you to draw the resultant vector, what do we do? Same way here. XL minus XC is 0, right? So the net opposition shown by both L and C will be 0. So who is the only one who is opposing now? R. It offers C. So R dominates. So at very low frequencies, therefore, since you know that capacitor is dominating, you can say current leads. At very high frequencies, current lags. And at this frequency, since resistor is dominating, current is in phase. And all the formulas are here. The voltages are added very beautifully, let us know. So because this comes from this graph, maybe the phasor diagram, if you are drawing anytime, I don't know, I can draw it along this one only. Let's say this is my voltage across R. Then current and voltage across R are in phase. Current through resistor and voltage across resistor are in phase. And current leads the voltage across C. And current lacks voltage across coil. And if I say that this is VL minus VC, assuming that VL is more than VC, then we have this resultant. This is your applied voltage V. What is the relation between this V, VR, and this much is VL minus VC? So that is here, Pythagoras theorem. V square is equal to VR square plus VL minus VC the whole square. And that gives me this equation, which gives me I is equal to V by Z, no? Where Z is equal to root of R square plus XL difference XC the whole square, called the impedance. Impedance has both resistive part as well as reactive part, which means it is the total opposition offered by R, L, and C to AC. Total opposition offered by the resistor, capacitor, and coil to AC. And yes, the angle by which the current leads or lacks is given by this expression, XL minus XC, or XL difference XC divided by R. And the values of phi surely will be between 0 and 90 degree. Resonance. And resonance, I told you when it happens at a particular frequency called F is equal to F naught, wherein XL becomes equal to XC. The phase difference is 0, because tan phi, we said, is equal to XL minus XC by R. XL is equal to XC, no? And you must be knowing this formula also, shortcut, no? XL is equal to XC can be calculated using root of L by C. Unit of all this is ohm. Unit of all this is ohm. Okay, so tan phi is equal to 0 means phi is equal to 0. XL minus XC is 0 means XL is equal to XC means XL is 0, right? So which means tan phi is 0. And tan can be 0 only for phi is equal to 0. What about Z then? Z becomes R. Why? Z is root of R square plus XL minus XC the whole square, which is 0 square now. The root of R square is R. And yes, you can calculate this resonant frequency using the formula. F naught is equal to 1 by 2 pi root LC. And that comes because XL is 2 pi FL, which is F naught L now at resonant frequency, is equal to 1 by 2 pi F naught C. And you cross multiply, you calculate for F naught will be this. Sharpness and bandwidth. The sharpness of resonance curve is measured using the factor called Q factor. Q factor means quality factor. So if I ask you a question, which two graphs are sharper here, graph 1 or graph 2, you will say definitely graph 1. But both have same values of resonant frequency, F naught. Which means F naught is decided by whom? 1 by 2 pi root LC. Remember, only L and C decides the value of F naught, not R. So which means curve 1 as well as curve 2, they use the same values of L and C. But what has changed maybe is the value of R. If R is less and less, current at resonance will be more and more. And the curve also becomes more and more sharper. So R is too small means Q is very large. And that means more sharper is the resonance curve. Okay. And yes, we can find out the Q factor. Q factor is always defined at resonance. And at resonance, we can always calculate the Q factor using the formula. XL by R is equal to XC by R. This is XL by R. Omega naught L by R means XL by R. Which is also equal to here one more formula. 1 by R root of L by C. Because you all know, I told you in the previous slide, what is the value of XL and XC? It is root of L by C. And therefore, it is 1 by R root of L by C. and it has no dimension, no? It's a dimensionless quantity. And yes, whether Q and bandwidth are related, yes, it is F naught by bandwidth. And bandwidth also has got a very fantastic formula. Bandwidth can be always calculated using the formula R by 2 pi L. Of course, bandwidth is also calculated from this formula, like, if this is I naught, and by root 2 you have to do, correct? Or power if you are taking whatever by root 2. These are called half power points. These are called half power frequencies, F1, F2. Therefore, F2 minus F1, the difference between the two half power frequencies is always the bandwidth. It's a range of frequencies over which the current is almost a constant. Yes, lesser value of R means bandwidth is small, sharpness is large, curve is more sharper. Q is large and the sharpness is more. Correct, no? See, I draw one more curve here. Very sharp it is. So you will find that bandwidth will be less, no, for this. Because R is very high, small. If R is small, only current goes on increasing, right, at resonance. So in a series LCR, R has a role of restricting the current at resonance. L and C restrict the current at other frequencies, not at resonance. At resonance means one particular frequency F naught. Okay. So you have understood now, therefore, who decides whether current leads or lags in LCR circuit? It is the frequency F does everything. At a particular frequency called resonant frequency, circuit is purely resistive. Otherwise, the circuit is always reactive. When the circuit is reactive, it can be either capacitive or inductive. When it is capacitive, for a frequency F less than F naught, circuit is always capacitive. For a frequency F greater than F naught, circuit is always inductive. Because at higher frequencies, XL becomes greater than XC and coil controls. Okay. So power, once again, this is the general definition of power in AC. Average power is equal to the product of apparent power into power factor. Apparent power is this, and the power factor is this, cos phi. And yes, cos phi at the resonance will be always equal to unity, and therefore, because Z is equal to R, no, at resonance. Cos phi can be always calculated using the formula R is equal to R by Z also. And Z is equal to R as resonance. Therefore, cos phi is unity, and the average power is the maximum power dissipation by a resistor, no? Vrms into IRMS. That's what we know. Power in a pure resistor, average power in a resistor. V0, I0 by root 2 we said, 2 we said, which is nothing but Vrms into IRMS. And this is what I said initially itself, current flowing through a pure resistor or pure capacitor or inductor is called as pathless current, because average power consumed is 0. Correct? Choke is a high inductance coil. Now, why we are using choke in AC at home? To restrict AC current. Because it dissipates less power. Because it has got resistance. Definitely no coil is there without resistance. So therefore, but the resistance is small. So coil is preferred, always when it is AC to restrict current, because it does not only restriction of current, it also consumes less power. Our average power consumed by the coil over the entire cycle is 0. LC circuit, it is also called as tank circuit. Tank because it saves energy. The amount of energy stored in a capacitor is always half CV square at any instant. Here it is half Li square. All right. And you know that at any point of time, energy stored in the tank is nothing but the sum of the energy stored in capacitor and coil. And the charge stored in the capacitor and the current are not in phase anytime. They're out of phase by 180 degrees. This is current graph. Of course, cosine graph, Q graph is this. Is a cosine graph. So Q is equal to Q naught sin omega, cos omega t, as I will be equal to I naught sine omega t, which means your cos omega t and sine omega t. This says that they are not in phase. So cos omega t can be written as sine of omega t plus pi by 2, no? Whatever. Okay, that means the phase difference is by an angle 90 degree. So this is tank. The advantage of connecting a coil in parallel to a capacitor is always to generate, this oscillations. But what we get in this is damped oscillations. Damped oscillations means oscillations whose amplitude goes on decreasing and finally it dies out because there are losses in the tank, losses in the form of invisible radiation, and yes, these wires have got resistance, therefore dissipation of energy in the form of heat. So there are two losses here, invisible radiation and heat loss, and that's how the oscillations keep dying. Otherwise, you should get sinusoidal oscillation, no? So that's why this circuit is very important, tank circuit. It gives you sinusoidal oscillations, and every oscillator circuit, uses if it is a LC oscillator, uses this tank. All right, this is transformer now. You know the primary and secondary of a transformer, the role of a transformer also, the role of transformer is, to isolate the two circuits, the primary circuit from the secondary circuit, without much loss in power. That's what we wanted. So we have this equation for a transformer, ideal transformer, IP by IS is equal to Vs by Vp is equal to Ns by Np. In fact, Ns by Np is equal to Vs by Vp is known as the turns ratio. If they say turns ratio is 1:4, you should understand that it's always Ns is to Np is 1:4. But it is equal to Ip by Is, because power is always eta, output power by input power. It is Vs by Is by Vp into Ip. This is efficiency, ratio of output power to input power, and the efficiency will be 1 or 100% only when Vs by Vs Is is equal to Vp Ip, no? That means when the output power is equal to the input power, and that can happen only when there are no losses. But then, you all know in transformer there are four types of losses: losses due to winding, the resistance of the winding, the losses due to the way in which the two wires are wound, flux leakage, therefore, the eddy current loss because of the transformer core, correct? And that's why to minimize the eddy current loss, we laminate the core, and the type of material used for the core, because of which there is hysteresis loss. And that's why soft iron core is also preferred to minimize the hysteresis loss. But there are losses, for which case Vs output power is always smaller than the input power. So the ratio of output power to input power, we expect it to be 1 in ideal transformer. Ideal transformer, it is 1. If it is 1 means what is Vs by Vp? It has to be not Is by Ip. No, it has to be Ip by Is. Therefore, for an ideal transformer, Vs by Vp is equal to Ip by Is is equal to, Ns by Np. So types of transformer, we have step up, step down, and isolation transformer. In isolation transformer, Ns is equal to Np. In step up transformer, Ns will be greater than Np. In step down transformer, Ns will be less than Np. If the number of turns in the secondary are less than the number of turns in the primary, it's called step down transformer. Okay. If the number of turns in the secondary are more than the number of turns in the primary, it's called step up transformer. Yeah, the step down and step up is always based on the voltage, AC voltage to be stepped up or stepped down. Transformer name itself says it is used to transform AC. So AC voltage or AC current is transformed. But in an isolation transformer where Ns is equal to Np, neither voltage is stepped up nor current is stepped up, but only isolation is provided between the primary circuit and the secondary circuit. So as I already told you, these are the two losses depending on the wire and windings, and these are the ones which are due to the core that we use. So to minimize this eddy current loss, we go for a laminated core, I said. And to minimize the losses due to hysteresis, we select a particular material, and that is made up of soft iron maybe. Okay. And to minimize the flux leakage, we go for tight coupling. Okay, it's two wires are wound one over the other so that entire flux linked with the primary is also linked with the secondary. To minimize the heat loss, we use good gauge wires. Okay, right. That's it from my side with regard to AC. I'm open for few questions. Yeah, you can either unmute and ask a question, or you can write the question in the message box. I don't know whether there is any message box available in this Cisco WebEx. Remember, suppose in case if I ask you now, if V is equal to V is equal to V naught sine omega t plus pi by 4 is the applied voltage through R, and write the expression for current. Current will be I is equal to I naught sine of omega t plus pi by 4. Because there should not be any phase difference between current and voltage when it is applied to R. But if the same voltage is applied to not R but L, then you should know that voltage leads the current. That means current lags. Correct? No. So current will be I naught sine of omega t plus pi by 4 minus pi by 2. What to do? And find out. So that's what you are supposed to write here. Okay. So that's how we have to go on doing and find out the expression for current. If it is C, then definitely current will not lag, but it has to lead. Therefore, sine of omega t plus pi by 4 plus pi by 2. This is what is given. So it has to be added. So this is what you need to also know. So a lot of questions are possible, in AC, interesting 1 or 2 mark questions. But if you know the theory, if you have a strong theory, then you can answer them all well. Yeah, I'm done. Go to KSTA center.
ವಿದ್ಯಾರ್ಥಿಗಳೇ, ಏನೇ ಕ್ವಶನ್ಸ್ ಇದ್ರೆ ಇವತ್ತಿನ ಉಪನ್ಯಾಸ ಕಾರ್ಯಕ್ರಮದ ಭಾಗದಲ್ಲಿ ಸರ್ ಇಲ್ಲೇ ಇದ್ದಾರೆ, ನೇರವಾಗಿ ಕ್ವಶನ್ಸ್ ಕೇಳಬಹುದು. ಏನೇ ಡೌಟ್ಸ್ ಇದ್ರು ಕೂಡ ನೀವು ಡೌಟ್ಸ್ ನ ಕ್ಲಿಯರ್ ಮಾಡ್ಕೊಳ್ಳಿ.
Good. In case if they have any questions, they can always ask me. This is my number.
Please note down the number.
Or you can mail me. When mailing is difficult these days, you can text me.
Later on mail ಮಾಡಿದ್ರೆ ನಾನು ನಿಮಗೆ ಮೇಲ್ ಮುಖಾಂತರ ಕಳಿಸ್ಕೊಡ್ತೀನಿ ಸರ್ ನಾನು.
Yeah, sure. Sometimes if they don't have questions right now, you can refer and write the questions later. I'll be happy to answer them.
Okay, thank you, sir.
Thank you so much, sir.
So anyway, today's talk on alternating current. So this is a very wonderful and informative talk on ಆಲ್ಟರ್ನೇಟಿವ್ ಕರೆಂಟ್ ಮತ್ತೆ ಮಕ್ಕಳಿಗೆ ಬಾರಿ ಸರಳವಾಗಿ ಅವರ ಇದಕ್ಕೆ ತಲುಪುವಂಗೆ ಬಾರಿ ಸರಳವಾಗಿ ಮಾಡ್ಕೊಟ್ಟಿದ್ದೀರಾ ಸರ್. ಸೊ
Thank you, sir.
KSJ and myself, once again thank you sir.
Sure, sir. Sure. Pleasure. Anytime.
So once again I thank to our Chief Executive Officer Dr. Ramesh sir and our Director A.V. Basaraja sir and all the attendees, lecturers and teachers. Once again I thank all of you. Thank you sir. Thank you very much.
Thank you, sir. Thank you.
ನೆಕ್ಸ್ಟ್ ಟೈಮ್ ಏನಾದ್ರೂ ಇನ್ನು ಮತ್ತೊಂದು ಕ್ಲಾಸ್ ಏನಾದ್ರು ಇದ್ರೆ ತಮಗೆ ನಾನು ಒಂದು ವಾರ ಮುಂಚಿತವಾಗಿ
ಖಂಡಿತವಾಗಿ.
ತಿಳಿಸ್ತೀನಿ ಸರ್.
ಖಂಡಿತವಾಗಿ. ಖಂಡಿತವಾಗಿ. I'll be happy.
Thank you all of you. So dear students, ಸೋಮವಾರ 4ನೇ ತಾರೀಕು ಸೋಮವಾರ ದಿನ ಡಾಕ್ಟರ್ ಚೈತ್ರ ರವರು ಕಾರ್ಬೋಹೈಡ್ರೇಟ್ಸ್ ಬಗ್ಗೆ ಉಪನ್ಯಾಸ ನೀಡಲಿದ್ದು ತಾವು ಎಂದಿನಂತೆ ಹೆಚ್ಚಿನ ಸಂಖ್ಯೆಯಲ್ಲಿ ಹಾಜರಾಗಬೇಕೆಂದು ಅಕಾಡೆಮಿ ವತಿಯಿಂದ ಮತ್ತೊಮ್ಮೆ ತಿಳಿಸುತ್ತಿದ್ದೇವೆ. ಥ್ಯಾಂಕ್ ಯು ಆಲ್ ಆಫ್ ಯು.